Welcome to all. This is Quality Enhancement in Engineering Education, that is QEEE, which is an initiative by MHRD, Ministry of Human Resource Development, Government of India. So under this QEEE, today I am going to start my course module on the topic Earth Pressure on Retaining Structures. This module will consist of altogether 6 hours of lecture, including the problem solving, assignments, etc. So today we are discussing the lecture 1 of this module, Earth Pressure on Retaining Structures. My name is Dipankar Chaudhary. I am going to discuss on this topic today. Currently my affiliation is I am with Department of Civil Engineering at IIT Bombay in Mumbai, India. For this course, before I start, I want to acknowledge this institute and student. Like, first of all, this is the picture of IIT Bombay and where from I am coming currently. And first I want to acknowledge the help provided by Center for Distance Engineering Education Program, that is CDEP of IIT Bombay, for making this facility available for today's QEEE program telecast and recording. Then my sincere acknowledgement to my Department of Civil Engineering of IIT Bombay, for facilitating all the facilities regarding my teaching and research at IIT Bombay. And finally, the main person who has helped me to prepare some of the slides of today's lecture and subsequent another 2 days lecture, that is my current PhD research scholar, Mr. Shubhrajit Moitra of IIT Bombay. So when we talk about the earth pressure on retaining structures, first of all, what we should understand that what is earth pressure and what are the various theories behind earth pressures. So let us have some introduction first. Like, whenever we get a soil mass below the ground, we say that it is stable when the slope of the surface of the soil mass is flatter or shallower than the safe slope of that soil mass. That we know that suppose if an existing ground of this profile, which I am showing over here now. So this is a profile of a ground. So this is any depth below the ground. This is a very shallow slope which I have drawn. So obviously this is a stable profile. Whereas this profile of ground may not be that stable because it is very steep compared to its horizontal inclination. So what it says that whenever we want to have some kind of level difference in the ground, suppose my ground surface at one side is like this and another side is like this, what we can achieve by the means of a slope like this. But this slope has to be stable, or this inclination which maintains the two different level of the ground surface has to be stable, provided this angle of inclination is very shallow or it is considering the soil properties. But due to the limitation of the available space, many cases, and mainly in the urban areas where there is a severe space crunch, we cannot have this much of extra space. This is nothing but what we require, an additional space to have the stability of this inclination. So what we can suggest in such case, suppose if we want to maintain the same level height where there is a severe space crunch, so to maintain this kind of two level difference of ground surface, we need to provide some kind of supporting system here which maintains the stability of this kind of level difference adjacent to each other. So this is nothing but what we call as retaining structure. So this kind of construction, so this can be of masonry, can be of concrete, any kind of rigid material. So this kind of structure which provides support to maintain a level difference of ground is nothing other than we can call them as retaining structure. So coming back to this slide here, you can see that at some locations, due to the limitation of space, it is not possible to provide that flat slope, that is the whatever horizontal extra distance you require, it is not able to be available or able to be provided at the site. So in such cases, a retaining structure is essential to construct to provide the lateral support to that soil mass. So that is what I have shown just now to you. So a retaining structure, it can be either permanent structure to maintain that level difference forever, or it can be a temporary structure, that is for some temporary reason we want to maintain a level difference, and once the work is done we can probably put or reduce the level difference, so then the need for the retaining structure is not there. So in that case we can call them as temporary structure. But anyway, the purpose of providing that is nothing but to provide a lateral support to that soil mass. So the design of this retaining structure, it requires a knowledge of the lateral pressure which is coming from the soil mass in such case. So what we can see, you can look at this example slide over here. It shows that various types of retaining structures, like retaining structures can be retaining wall like this, what I have also drawn on the paper, and the slide what I am showing, to maintain an embankment over here at a very different level than your conventional ground surface, which is at much lower depth like here, or to maintain a cut, vertical cut. So this is your natural profile of the soil, and we want to excavate and make available a cut portion like any underground construction, metro, etc. So there also you need this kind of lateral supporting system or retaining structure. It can be sheet pile wall, it can be anchored bulkhead, it can be sheeting and basement wall, etc. So some more examples of the retaining structure, for example like bridge abutment, like this is the bridge and this is the natural profile of your ground. So you maintain the level difference over here. To do that, to provide the support at this end, you provide this kind of structure which is nothing but retaining this portion of the load coming from this soil. Again, the flood wall, that is to protect the shoreline from the ocean wave or sea wave. Generally we provide this kind of wall, rigid wall, which can support the ocean wave or sea wave or the water pressure like this, to protect this kind of the portion of the ground. So essentially there is a level difference, and in addition to that you have a water pressure acting on this side. Then water storage also, this kind of system you need all around this retaining structure. And for a flexible type of retaining structure, I will come to that little later. So these are essentially rigid type of retaining structure, and this one where the section of the wall, section of the retaining structure is very small compared to its depth or length or height. In that case, it will behave as a flexible retaining structure, for example sheet pile wall or diaphragm wall, and this is the anchored sheet pile wall with a ground anchorage like this. So in coastal region we have several such kind of construction where sheet pile wall or diaphragm wall are get constructed, and these are nothing but classical examples of various types of retaining structures. So now coming back to this slide here, you can see in this slide what is lateral earth pressure. If we look at the slide, it says that the pressure or the force which is exerted by the soil on any boundary is called as earth pressure, boundary of that wall or retaining structure and the soil. So when the earth exerts a pressure on the side or back or the face of that retaining wall, that is nothing but we call them as lateral earth pressure. Now you can see here the magnitude of the lateral earth pressure, it depends on the movement of the retaining wall, which is relative to the backfill and based on the nature of the soil. So that decides what type of earth pressure is coming into picture. So let us see in this document camera now. So which I have drawn earlier, what I am telling that the lateral earth pressure, if we take any particular soil mass at a depth, say Z, from this ground surface, now I have vertical stress acting on this soil mass over here, assuming these are principal planes, and I have some stress in this direction or lateral direction, let us say a horizontal, sigma h. So this sigma h will obviously act here on the soil mass to maintain equilibrium, and that in turn will act on your wall, which gives a lateral pressure to the wall. So for this kind of any soil mass, if we take this soil element, how this causes the lateral earth pressure we have understood. Now let us see what are the different types of this lateral earth pressure or this sigma h can be depending on the movement of the wall. So if we now check that there are three different types of lateral earth pressure. Remember, in this case, one essential comment I would like to maintain or mention over here, this is, I am talking about a soil element. So this is a soil element. So this sigma h, which I am talking about the lateral stress or horizontal stress, principal stress, this is because of the soil material, not due to the water or any other thing. So whenever we are using the terminology earth pressure, we have to be very sure that this is the pressure exerted by the earth or soil. It is not the water pressure if there is a presence of water. So in case of dry soil, of course, it is the total pressure is equals to earth pressure. But if it is a moist soil or water table is within this layer, then the total pressure will be combination of earth pressure plus water pressure. So what are the three types of lateral earth pressure? Let us write down now. So these are active earth pressure, the second type of earth pressure is called passive earth pressure. Remember, for the case of passive, we also use another nomenclature which is known as passive earth resistance. I will come to that in a little while. Why this terminology? Actually, this is a better terminology to use resistance rather than pressure for the case of active earth condition. And the third type of lateral earth pressure is none other than at rest. So at rest earth pressure. Now if we start understanding what are these different types of earth pressure and coming from where, if you look at this term at rest, it automatically says that what type of earth pressure it can be. It says that the wall, this is not moving, it is at rest condition. That means there is no movement, no deflection, no further lateral or rotational movement of this wall. Because of that, whatever lateral stress is coming here, that is nothing but earth pressure at rest, because your wall is at rest condition. Now what is active? How that active condition is coming? So active earth pressure is nothing but, if you see over here, Due to this level difference, this side of the earth is exerting a pressure on this wall. So there is every possibility that the wall may shift towards this side. So this is the displaced position of the earth, and that deflection or movement, let us say delta. And if we say that we want to maintain the level difference between two ground is capital H, which is also called height of this wall. So this value of delta by H is very important to know which type of lateral pressure is acting on the wall. Now, as I have shown, the soil is exerting pressure on the wall, hence it has moved in this direction. So this delta by H in such case where the wall moves away from the backfill, this soil is called backfill, is known as active state of earth pressure. So this condition where the movement of the wall is in this direction, so this is the direction of movement of wall from this backfill soil, that is called the active state of earth pressure. Now why this active state comes into picture? Let us understand this from the concept of mechanics through the use of Mohr circle. So before I start that, let us look at the slide here. So if we look at the slide, the lateral earth pressure is usually computed using classical earth pressure theories which were proposed by Coulomb in 1776 and by Rankine in 1857. These two are classical earth pressure theories, and the general wedge theory was proposed by Terzaghi in 1943, which is more general and it is an improvement over the Coulombic and Rankine earth pressure theory. So different theories of earth pressure, as I said, two classical theories are Coulomb's earth pressure theory and Rankine's earth pressure theory, and we will first try to see that active and passive state of earth pressure using these theories. Now, if we want to know what are the fundamental assumptions of any earth pressure theory in general, we can mention that in like most of our geotechnical problems, some of these assumptions are always valid. Here as well, it is true for theory of earth pressure, like soil mass is considered as semi-infinite, homogeneous, isotropic, dry and cohesionless soil. So basically the theory of earth pressure by both this conventional earth pressure theory or classical earth pressure theory of Coulomb and Rankine were proposed for cohesionless soil, that is mostly sandy kind of backfill material, and for dry condition. But later on these were extended for general C5 soil or cohesive soil also, and moist condition, all those things. But these are the fundamental first assumptions in these theories. The ground surface is considered as a planar surface, and which is initially considered as horizontal, then further extended as inclined. The back of the wall is considered as smooth and vertical, but this assumption is only correct or only applicable for the case of Rankine earth pressure theory. For Coulomb earth pressure theory, this assumption is not valid because Coulomb considered any inclined wall and also a rough wall. The soil mass is in the state of plastic equilibrium. What is plastic equilibrium? That is, the soil is no longer in its elastic behavior. It has attained its plastic state of equilibrium, that is at the verge of its failure. So well drained to avoid consideration of pore pressure is an inherent assumption in deriving the earth pressure theories, and if it is not, then additional pressure due to water needs to be considered. Now, as I have already mentioned, the three different types of earth pressure coming from like at rest condition of earth pressure, when a retaining wall with a plain vertical face which is backfilled with a cohesionless soil, and if the wall does not move even after filling the material, then whatever pressure the soil exerts on the wall is known as at rest condition earth pressure acting on the wall. Whereas for active state of pressure, if suppose the wall is gradually rotated or moves away from the backfill soil, then the unit pressure acting on the wall gradually gets reduced. So in the case of active state of earth pressure, as the pressure initially the soil started giving on the wall, that slowly gets reduced. Why it gets reduced? It is quite obvious from the picture which we have shown here earlier. You can see over here, like initially when wall was at this position, this red color, the soil laterally was giving certain amount of pressure. Now when due to that pressure wall has moved in this direction, that is away from this backfill soil, then obviously to maintain equilibrium this pressure has slowly reduced till it reaches its verge of failure state or the plastic state, which we have termed as active state. Now let us go back to the slide again. So you can see here that the unit pressure on the wall gradually gets reduced, and after a particular displacement of the soil at the top, the pressure reaches a constant value, and this pressure is the minimum possible pressure which the earth can exert or give on the wall, and that is known as active state of earth pressure or active earth pressure. Typically we use the symbol for the active thrust, the total force, P suffix A. Whereas for the passive earth pressure, we, as I have mentioned, we should call it correctly as passive earth resistance. What is that? This is the situation I have already explained when your wall moves out from the backfill side in this direction. It can be lateral, it can be rotational, it can be combination of these two, and that it reduces this lateral pressure, and subsequently we reach a minimum possible value acting on the wall, that is our active state of earth pressure. But in some cases when the wall moves towards the backfill, that is now what happens, that wall is putting extra pressure on the soil. So wall has moved towards the soil or towards the backfill. It can be again either rotation or lateral deformation or combination of these two. In that case we call whatever pressure is coming from the soil side, that we call as passive earth pressure. Or why I said it is better to call it passive earth resistance, because this is the resistance which is provided by the soil to the wall. So that's why the name passive earth resistance is a better terminology for this. And what will happen in that case? When the wall moves towards the backfill, the pressure on the wall keep on increasing because it is pushing towards the soil. So then from the rest condition it reaches a higher and higher value till it reaches at the verge of failure or plastic condition. So that is maximum possible value, and that maximum possible value is called as passive earth pressure or passive earth resistance. So now let us understand this entire process through the mechanics. That is, if I take a soil element at any depth, you can now see in this document camera. Yes, so if you see here, this soil element is subjected to a vertical stress sigma V and the lateral stress of sigma H, assuming these are principal plane. Now if I want to draw this state of stress in the soil through Mohr circle, what I can do here, let us look. So this x-axis my normal stress, this y-axis the shear stress, and if I assume initially that sigma V, that is vertical stress, is greater than sigma H initially, starting with that condition I can plot the values of sigma V here and I can plot the value of sigma h here. Now when there is no movement of the soil or that wall, in fact the interface, then this we have mentioned it as earth pressure at rest, and this is the portion of the Mohr circle. We can draw like this. Now remember, if it is a C phi soil, that is if the soil media which I am considering below the ground surface over here, let us so essentially for this height of wall, now if I say that there is no movement of the wall, I can draw this sigma v and sigma h, and if I say this is a C phi soil, that means cohesive and frictional soil, then the failure Mohr Coulomb failure envelope I can draw like this, which is, this is C and this is our phi, as we all know. So what will happen in this case? You can see over here. Now wall started moving away, I said in the first instance, wall is moving in this direction by that delta amount in this side. So this sigma h has to reduce because you are releasing the pressure by movement of the wall. But sigma v, is there any change to that? No, because this is vertical stress at any depth z that remains unaltered. There is no change in the value of your sigma v. So this point remains same, but the sigma h keep on reducing as your wall moves away from the backfill. So because of that, if we keep drawing the various state, till which value this sigma h can reduce? Until it touches this Mohr Coulomb failure envelope. That means when it touches this one, whatever value here we get for sigma h, that is nothing but our active state of earth pressure. So I can mention it as sigma a. So that is nothing but what we have mentioned as it goes to the plastic state of equilibrium. So this is my active state of earth pressure, the lateral pressure, and this is my vertical stress. Now this active state, if I want to find out what inclination of the failure plane with respect to the various direction, what we will get. So this point on the failure envelope I can connect with these two ends. So whatever is the angle of this, that will essentially give me the inclination of failure plane with respect to the horizontal. Why it will give me that? Because as we all know from the concept of Mohr circle, that first we have to identify the pole of the Mohr circle. Then any change of stress or finding out the direction, planes, everything should be with respect to the pole. So if we want to find out what is the pole for this active state, you can see how to find out the pole. Like sigma v is acting on horizontal plane, so we should draw a horizontal line through the sigma v, and the sigma h is acting on a vertical plane, so we should draw a vertical line or vertical plane for that sigma h. In this case, suppose if we have taken sigma a at that point, so wherever these two plane meets, that is nothing but the pole of the Mohr circle. In this case, this is our pole. This point A is our pole. So that's why if you find out this angle alpha from this pole with respect to failure envelope with respect to horizontal, that alpha value gives us the inclination of the failure plane. Now how much is the value of this alpha? This value of alpha I will calculate little later. Now let us understand the other state of movement of the wall. Now in the second state of movement of the wall, if suppose wall starts moving in this direction, that is wall is going towards the backfill soil, this red color now I am using, what is happening? Your lateral stress is keep on increasing because wall is pushing towards the soil. but again there is no change in the vertical stress. So the sigma V remains constant, but sigma H keep on increasing, and it increases from this sigma H of at rest condition, and then it increases and goes to the other side, because sigma H now increases over sigma V, and till which time it can increase? It can increase until and unless this Mohr circle also touches the failure envelope. So when it touches the failure envelope over here, that gives us the plastic state, and that point here we can term it as sigma P. That is, this is the lateral pressure at passive state or passive condition. Now if we connect this point with respect to this and with respect to this, we will get the inclination here. Let us say this is beta. This beta inclination with respect to horizontal, that will give me the inclination of the failure plane, because these are nothing but failure planes. It only depends in which direction you are taking. Now for this second set of Mohr circle for passive state, if we want to find out what is pole, because again it is important, that will give us the direction of which plane we should consider, whether this line or this line. You can see sigma V is acting again on horizontal plane, and sigma P, or this lateral stress, is acting on a vertical plane. So we should draw a lateral vertical line here, horizontal line, wherever they meet together. So that point gives us the state or the pole. In this case pole B is for the state of passive earth pressure. So this is simple Mohr circle explains how the active state and passive state of earth pressure at plastic equilibrium condition or at the verge of failure is getting formed due to the movement of the wall away from backfill or towards the backfill. So now coming back to this angle of inclination of alpha and beta, we all know about it, but still for the sake of completeness I can always mention it, that alpha is equals to 45 degree plus phi by 2. So this is the inclination of this alpha, whereas for passive case the angle beta is 45 degree minus phi by 2. So if we take this plane and plot it according to the stress plane directions, what we will get, let us skip this and draw it in the next page to further understand it through the concept of the stresses. So in the state of active condition, what happens to the ground surface with respect to the stresses? Look at here, the vertical stress here, which is higher for the active state. So sigma, in this case sigma V is greater than sigma A. So I can always say that the sigma V can be called as major principal stress and sigma A is our minor principal stress, right? So typically we can use the symbol sigma 1 for major principal stress, sigma 3 for minor principal stress. Whereas for passive state, what happens? You can see here clearly that sigma V is less than sigma P. So what happens in this case? In this case, sigma V is nothing but the minor principal stress and sigma P is nothing but major principal stress. Okay, so with respect to which stress direction this angle of inclination occurs, let us see. So for active state, we already obtained that inclination of the failure planes which are parallel to each other, because as you can see from this diagram, this is valid for any soil element. So number of soil elements, the same parallel planes you can always draw. So these are set of parallel planes which are inclined at an angle with respect to horizontal at an angle of 45 degree plus phi by 2. So this is called the inclination of the failure plane for the case of active state of earth pressure. So this is for active earth pressure condition. For the other case, if I draw the same failure pattern, what I will get for passive case, let us see. So in this case, our inclination of the failure plane will be flatter than what we got in the active state, with this angle with respect to horizontal as 45 degree minus phi by 2. So this is for passive earth pressure condition. Now with respect to horizontal, this one we have seen from the Mohr circle. So that's why we can mention it here, that in this case with respect to horizontal active state, 45 plus phi by 2 is your inclination of the failure plane, because this is your pole, whereas for passive state this is your pole. So that's why inclination of the failure plane is with respect to horizontal is 45 minus phi by 2. Now if we want to generalize this or remember only one single thing, you can always say that for active state, what is our major principal stress direction? So this vertical stress or vertical stress direction is our major principal stress direction. Okay, whereas for passive condition, your major principal stress direction is in this lateral direction. So this is your major principal stress direction. So what happens in this case? So major principal stress direction, but which is your major principal plane? Major principal plane is your this. That is the lateral one on which the major principal stress is acting. So 45 plus phi by 2 is always the angle of failure plane with respect to the major principal plane, because in this case we can see this is our major principal plane, and in this case our major principal plane is nothing but the vertical, because this lateral pressure acts on the vertical axis. So the vertical plane is nothing but our major principal plane. So with respect to major principal plane, what is the angle? This one, this is same as 45 plus phi by 2. So in generalization, we can always say that inclination of failure plane are at an angle of 45 plus phi by 2 with respect to the principal plane. So if we remember whichever is the major principal plane, so whichever is our major principal plane, with respect to that always our failure plane is inclined at an angle of 45 plus phi by 2, whether it is active state or passive state. So that way we will never forget that whether it is active condition or passive condition, because we know the major principal stress and major principal plane are different in both the cases. Now if we come back to this slide over here, you can see now this slide that development of that active and passive earth pressure condition because of the movement of the wall. Now movement of the wall, how much and in which direction? Which direction we have seen already that delta A is away from the wall. Suppose if we say this is our reference plane, that is at rest condition, when there is no movement of the wall, and this side it shows the movement of the wall away from the backfill or far going away from this backfill side or soil side, and this side denotes the movement towards the backfill or into the backfill. Then for active state we have seen that from at rest pressure, when there is no movement of the wall, pressure is at rest, which generally we denote as P suffix naught, P naught condition, or the corresponding earth pressure coefficient we call as K naught. So now when we go away from the backfill, we said the lateral pressure keep on reducing. So which finally goes to the plastic state at the verge of equilibrium, and that minimum value we call it as active state. So you need this much amount of movement of the wall delta A, which is necessary to form this full active state of condition on the wall. Let us come back to this derivation once again. You can see clearly here, I was talking about the sigma V sigma H are for at rest condition. So when there is a reduction in the lateral stress, finally it touched the failure envelope and reached this active state. Now this active condition of earth pressure, it requires a certain amount of movement of the wall, and then only we can say it is a active earth pressure completely. Otherwise in between these various positions are partially active earth pressure. They cannot be called as a full active earth pressure. Similarly for the other side of the wall movement, that is when wall goes towards the backfill side, there is an increase in the lateral stress, and that also requires a certain amount of movement of the wall. Finally, as long as it reaches the verge of failure condition when it touches over here, and that condition we can call as fully passive condition of earth pressure. So in between whatever values you get here at these locations, these are none other than partially mobilized passive earth pressure. So these are not complete passive earth pressure. You need a certain amount of movement. So in this case we say delta A is required minimum wall movement to get the complete active state. In this case we say delta P is required the amount of wall movement to get fully passive condition. If your delta value is less than delta P, then it will be partially passive, and if your delta value is less than delta A, that will be called as partially active earth pressure. So these are in between. Now if we look at the slide here, so in the slide it shows that all this portion of the curve I am showing here now through this pointer, that these are the various states of partially mobilized active earth pressure, and these are the various positions which is shown in this curve. I am showing through this pointer. These are various locations where partial passive earth pressure is there. When it reaches that minimum required delta P value or the displacement required by the wall, then it reaches the full passive condition, and that is our passive pressure or passive resistance, P suffix P, that is the symbol we use. And here when it reaches the plastic state of equilibrium, that means after a movement of delta A, we call this as PA, that is P suffix A, or active state of earth pressure. So this is active state of earth pressure completely is the minimum among all these three pressures, that is earth pressure at rest and passive earth pressure and active earth pressure. Among these three various states of earth pressure, active state is the lowest value of the earth pressure which can act on a wall. So if as a designer of civil engineering, if we want to design any wall, we actually want to design it as active state. So that is the reason why active earth pressure theory is so important and so much applicable in the field, because we don't want to design it for a higher pressure, then if you want to design it for a higher pressure, what will happen? You have to design the wall section much thicker. You have to use more amount of reinforcement, cost of construction, everything will increase to resist that high value of the pressure coming from the soil. So at rest condition, nobody wants to design at site. Everybody wants to design for active state of earth pressure by allowing the wall to move by this nominal amount of required to mobilize the fully active state of earth pressure. So it is very important to understand whether that fully active condition has been achieved or not. If it is partial based on the displacement of the wall because of some restriction, then one can always ask, then what is the need for studying the other state of earth pressure? We can only study active earth pressure because, as I am telling, it is the most common, and we want to design for active state of earth pressure at site because there are certain type of construction or this level difference where you want to maintain what I was showing earlier to position some of your important structure where amount of displacement or amount of movement allowed is very, very negligible, close to zero. Suppose you are putting a very sensitive equipment or a machine foundation where the permissible limit of the movement of the foundation is very, very small, almost close to zero. In that case, you don't allow your wall to move in such condition of difference of level ground. If you want to maintain, then probably you have to go for design at the condition of at rest. You don't allow even the small amount of movement which will generate the active state of earth pressure. So this is the application of earth pressure at rest. There are many others also, but as I said, majority of application of retaining wall design is on the active side or active state of earth pressure. And for passive condition, there is extensive use of passive condition of earth pressure, but their usage for retaining wall is not that significant. Mostly we don't design it in such a way that soil will be weaker than the wall, or soil has to resist the wall force. We don't design like that, but it has an extensive application in the bearing capacity theory, in the anchor uplift capacity theory. So we will discuss those things when we will talk about the necessity or need for studying the passive state of earth pressure. Now again, coming back, I have already explained this slide. Let us now go back here. So when we are measuring the passive pressure, we are measuring the resistance of the soil. I have already mentioned it. So hence, for all practical purposes, we get fully mobilized active earth pressure, but the mobilizing the full passive earth pressure, you require a large amount of movement which does not always occur at site. You can see over here, delta A to mobilize active state is much smaller in the quantity of the movement of the wall compared to the delta P which is required to generate the passive state, which we have seen through the Mohr circle also. So therefore, we should design with PA value only with a difference of a small percentage of passive earth pressure. Why this concept comes? Let me explain now to this. So essentially, when we are trying to design a wall, let us say this is the rigid retaining wall which we want to design to maintain the level difference of ground and two sides, and obviously this is the typical embedment depth of the wall you have to provide to give the stability of the wall. So this is the height of the wall. Now what essentially will happen if your wall tends to move in this direction, or you allow, in this case because it is quite obvious this side soil because of level difference will put a thrust on this. So we have active state of earth pressure from this side, and because wall is moving away from the backfill, but for this backfill what happens? It happens that wall is moving towards the soil. So this side of the wall, it will be passive state of earth pressure. So in design, if we want to optimize the design or economize the design, the best way to take the resultant, that is PA minus PP, which will be, let us say, P resultant. We have to design for this P resultant lateral thrust and provide the section, reinforcement, everything accordingly. But as we have already mentioned, this amount of delta required for active state to form completely is very small compared to the value of delta P which you require for this passive state to form. That is the reason this full passive pressure, if you deduct, you will be grossly doing a mistake in your calculation of pressure. So it should be some fraction or some percentage of total passive pressure which you need to deduct. And how much is that percentage is not known completely. So many cases in design, people don't use this deduction of passive earth pressure at all. We only design for this active state of earth pressure for the wall, not for the resultant pressure. Now, if we move back to the slide, you can see here. So it shows clearly that we should have designed, theoretically speaking, for PA minus a small percentage of PP, but as we are making an unsafe design by designing if we do PA minus fully mobilized PP, and an uneconomic one if we only consider PP, but it is better to be safe using only PA rather than deducting a small percentage of PA until and unless we are sure that that much percentage of PP has been mobilized from the other side of the wall. Now what are these amount of movement of the wall? If we see, we will appreciate it much more. So to get mobilized fully active and passive state, the amount of wall movement which are necessary are of this order. That means delta A required is about 0.1 to 0.4% of the height of the wall, so which is very, very small. You can see. So that is the reason why at the field we can easily achieve the state of active earth pressure condition, which is good for us. I said because active state of earth pressure is minimum among all the pressures, and delta P, which is required to mobilize full passive earth pressure, is about 5 to 10% of the height of the wall. So which is much higher than the amount of wall movement which is necessary for active state. So for this amount of wall movement, the previous problem which I was showing, if you consider the full passive earth pressure, we will make a mistake. If we consider the corresponding partially mobilized passive earth pressure due to this movement, then also it can be questioned depending on the scouring effect and many other things in the bottom portion of the ground surface. So that's why we don't consider it at all most of the cases for conventional retaining wall design. I am telling here conventional or rigid retaining wall, but if we design flexible wall etc., we will consider this value that we will see later on. Why these ranges are given, you can see over here. For dense sand, this PA mobilized at a lower value of strain or lower value of movement, which is 0.1% of the height of the wall, whereas for loose soil it requires higher value of movement, that is 0.4%. Whereas for PP to get fully mobilized for dense sand, you require 5% of the movement of the wall, and for the case of passive you require about 10% of the movement of the wall. So this concept of movement of the wall and formation of active and passive state of earth pressure I have already explained through the Mohr circle, and also we have arrived at the inclination of this failure planes with respect to horizontal. Now let us come back to the third type of lateral earth pressure, which is nothing but earth pressure at rest condition. What is at rest? I say when there is no movement of this wall. So whatever pressure acts at this back face of the wall, that is at rest. Now at rest pressure, the sigma h lateral pressure, it can be expressed as some constant K naught or some coefficient, we call coefficient of earth pressure at rest times sigma v. So where from this has come? If we go back here, this document camera, you can see the relationship between the sigma v and sigma h. We can always mention that sigma h is some coefficient k times this sigma v. That we can always mention. So this k is called as coefficient of lateral earth pressure. So this is called coefficient of lateral earth pressure. So this coefficient of lateral earth pressure, we use three different symbols for three different state of earth pressure. What are those things? Let me bring it here. So the slide where I was mentioning the three types of earth pressure, now let me denote them. Total active earth pressure we denote by the symbol PA, P suffix A, and the corresponding coefficient of lateral active earth pressure we denote generally by Ka. For the passive case, we mention it by the symbol PP, that is total passive resistance, and the corresponding coefficient of passive earth resistance we denote it as Kp. And at rest we use the symbol P0, that is not because there is no movement of the wall, and the corresponding lateral earth pressure coefficient is nothing but earth pressure coefficient at rest is K0. So this K0 condition is nothing but at rest movement of the wall. Now coming back to the slide over here, you can see if the wall is rigid and does not move with the pressure which is exerted on the wall, the soil behind the wall will be in the state of elastic equilibrium, because it has not reached in the verge of failure, or it has not reached at the plastic state. It has not touched that Mohr Coulomb failure envelope. So that's why it will be under the condition of elastic state of force equilibrium, and because of that we have to establish what is the relationship or what is the equation what we will get for the coefficient of lateral earth pressure at rest K0 for this kind of situation. So if we mention that if we consider backfill soil is homogeneous with both sigma h and sigma v increases rapidly with depth, then the ratio of this remains constant, that is sigma h by sigma v is always sigma h by gamma z if you don't have any other surcharge or other thing. That denotes as K0, where K0 is coefficient of earth pressure at rest. So lateral earth pressure can be mentioned as sigma h equals to K0 times sigma v. As I said, if there is no other surcharge acting on the ground, then the sigma v is nothing but your gamma times h. So what will be the total pressure acting on the wall? That is earth pressure at rest. P0 is half K0 gamma h square. You can see from this figure, at any depth z, this value of the stress, lateral stress, will be K0 times sigma v. Sigma v is nothing but our vertical stress due to the soil. So vertical stress is nothing but gamma is the unit weight of the soil times this z, so gamma z. So K0 gamma z is nothing but the intensity at this level, and at the bottom of the wall, that is height of the wall is h. So here the value of that pressure will be K0 times gamma h. So if you take the distribution, this will be obviously the linear distribution like this, and the area of this triangle will give us the total pressure acting on the wall at rest condition, which is P0 is nothing but half this K0 gamma h into this h, so half K0 gamma h square. And where this earth pressure at rest will act, obviously this is a triangular distribution, so it will act from the base of the wall at h by 3 or 1/3 from the base. So the value of this K0, it depends on relative density of the sand and the process by which that deposit gets formed. So we will see that K0 value and their various definition and equations as far as the elastic equilibrium is concerned. So we were discussing that coefficient of earth pressure at rest condition K0, we already have seen that this is at the state of elastic equilibrium. So when we are talking about the state of elastic equilibrium, what we get, let us see. So if I draw a soil element, so for this three-dimensional soil element, let us say this is our sigma z, this is sigma x, and this is sigma y. Now for considering all these are principal plane, now sigma z we have denoted as vertical stress sigma v, and for our case sigma x equals to sigma y always, which is equals to sigma h, that is lateral stress. Now for this, what we have mentioned at rest condition of earth pressure. So at rest means there is no lateral strain, because that is the condition what we have defined by at rest, there is no lateral movement. So if lateral strain, these are the stress directions. If we say the corresponding strains are epsilon z, that is the strain in vertical direction, epsilon x, strain in x direction, and epsilon y is the strain in y direction. So no lateral strain means our epsilon x and epsilon y should be equal to 0, but epsilon z obviously will exist because it is not 0. So if it is so, what we can write here, like sigma x equals to sigma y, which is our sigma h, that we have already defined as k naught times sigma z or k naught times sigma v, that we have seen already. Now if we apply the theory of elasticity, what we can write down, that epsilon x, the strain in x direction, can be written as 1 by E times sigma x minus mu times sigma y plus sigma z. This already we know from our solid mechanics knowledge or theory of elasticity knowledge, that strain in x direction can be expressed like this, where E is the modulus of elasticity and mu is the Poisson's ratio of the material. So this is Poisson's ratio of the soil. So this is Poisson's ratio and this is modulus of elasticity. Because it is in the state of elastic equilibrium, so we can always consider this condition. Now what are the values of other strain directions, that is epsilon y and epsilon z? In the same way we can write epsilon y is given by 1 by E times sigma y minus mu times sigma x plus sigma z, and the z direction strain epsilon z will be written by 1 by E sigma z minus mu times sigma x plus sigma y. Now what we have seen, that epsilon x equals to 0 as well as epsilon y, because there is no lateral strain. So to do that, if you apply in this first equation itself, this equals to 0, what do we get? You can get sigma x is equals to mu times sigma y plus sigma z. So this gives us, I can write here itself, that sigma x is equals to mu sigma y plus sigma z, right? Now if I use that further, what we can write, that k naught times sigma z is equals to mu times k naught sigma z plus sigma z. How we can write this from the previous equation? That means sigma x equals to mu times sigma y plus sigma z, because we know sigma x is nothing but k naught times sigma z and sigma y is also nothing but k naught times sigma z. So this we can write. So if we simplify this further, what we will get, the k naught is given by mu by 1 minus mu. So this is the derivation of the expression for coefficient of earth pressure at rest condition, which is a function of Poisson's ratio. But remember, it is valid only for elastic material and for NC soil, that is normally consolidated soil. The value of mu is always will be less than 0.5 for soil, as we all know. So we will get a value here of K naught, which will give us K naught less than 1. Because as mu is less than 0.5, K naught will be always less than 1. So if it is water or very soft clay saturated condition where mu value is approaching towards 0.5, what we will get? That will give us K naught equals to 1 when mu is equals to 0.5. So essentially what it says, that lateral pressure given by water is same as vertical pressure, because sigma h is K naught times sigma v. So water gives all around equal pressure. This is another way of looking at it. That means from this concept also we can say that pressure in water all around is same, because K naught or that coefficient or lateral coefficient is 1 for the case of water. But if it is normally consolidated soil, then only this situation of K naught less than 1 occurs. If water is present in that, then K naught equals to 1 has to be taken care of. But if it is over consolidated soil, in that case this K naught can be more than 1 also. So where this K naught can be more than 1, let us write down here. So for OC soil, that means over consolidated soil, over consolidated we all know the soil which were earlier subjected to higher load or stress level. So various researchers have given various expression like K naught equals to 1 minus sine phi dash times OCR. OCR is nothing but over consolidation ratio. We all know that, to the power sine of phi dash. This is one expression of K naught for OC soil, over consolidated soil, which is given by Professor Kulhave and his research group. Another expression for K naught is 1 minus sine phi dash. Phi dash is nothing but the soil friction angle in drained condition or effective soil friction angle root over OCR. So this equation is given by Meyerhof. So this is mostly used in field or practice, which Meyerhof has proposed in around 1976. This is the equation for over consolidated soil. So in all such cases, K naught can be greater than 1, even much greater than 1, depending on your value of over consolidation ratio. Now there is another conventional equation other than this theory of elasticity to obtain the K naught. That equation, let me put it here. K naught is given by 1 minus sine phi dash, which is known as Yackey's equation. Yackey gave this equation obtaining the K naught, but again you can see this is for NC soil. To repeat, this Yackey's equation is valid for normally consolidated soil, or you can use this theory of elasticity also, but for over consolidated soil you have to use Meyerhof's equation or Kulhave's equation. Now let us come back to the slide here, which shows, you can see from elastic theory or theory of elasticity, K naught is mu by 1 minus mu, where mu is the Poisson's ratio, and according to Yackey, a good approximation one can find out K naught equals to 1 minus sine phi. All these are for only normally consolidated soil. So these are various values of K naught where all are less than 1, you can see, for the normally consolidated soil. Now let us again discuss in detail the active and passive state of earth pressures. And let us now first start with the conventional theory for earth pressure, that is Rankine's theory. So in the Rankine theory, you can see over here what are the various assumptions, like there is no wall friction angle. That means it is essentially considered the wall is smooth. That means the back face of the wall connecting to that backfill soil is a smooth wall. That's why there is no friction. So wall friction generally we denote by the symbol delta is 0, and wall is considered as a vertical wall. That is Rankine's first assumption. Then the ground and failure surface are straight planes. Failure surface we have seen it is straight plane. We have derived it that it is at slip planes or failure planes are 5 plus 5 by 2, always with respect to the major principal plane direction, and the resultant force acts parallel to the backfill slope. Soil is homogeneous and isotropic. So with these assumptions, what Rankine did, this is the vertical face of the smooth retaining wall and active state, so it moves in direction. This is the failure plane which is inclined at an angle of 45 plus 5 by 2 with respect to horizontal. So what are the forces acting on this failure plane is this weight of the failure plane, that is W, weight of the failure zone W. This is the earth pressure PA. You can see this is nothing but the resultant. Actually pressure is acting from this side. So we from wall side when we are drawing, we always draw it as a resistance. So PA, and this side is the interface soil friction force or resultant force is R, which acts at an angle of phi. Now if we take the equilibrium of these three forces, and these three are coplanar and concurrent forces, that means they passes through a single point. So you can always find out the equilibrium of these three forces by using this force polygon or force triangle in this case, and what you can derive that what will be the intensity of the pressure at any depth Z. So intensity of lateral earth pressure for cohesionless soil, that means if soil is sandy type, then PA at any depth will be that K, lateral earth pressure coefficient. In this case it is active, so that's why Ka times sigma V. So sigma V at any depth Z can be gamma Z, and at the base of the wall it will be gamma H. So total pressure on the wall will be area of this triangular distribution of the passive active earth pressure, where intensity here at the bottom of the wall is Ka times gamma H. So it is half Ka gamma H square, where this Ka coefficient of active earth pressure, which is called, is equal to tan square 45 minus 5 by 2. Now where from we got this value? Now I will explain it. This is very simple, and this PA, that means this resultant active earth pressure force, where it will act, because it is a triangular distribution of pressure, so it will obviously act at the 1/3 base height, that means from the base of the wall at a height of 1/3, so H by 3. Now coming back to the concept of major and minor principal stress, what we can write down, that for the soil element in active state we have sigma V here, we have sigma V here, and we have sigma A here. Now active state we are considering sigma A, sigma V. Now which one is major principal stress and which one is minor principal stress? This sigma V direction is our major principal stress, sigma A is our minor principal stress, that we have already seen. So based on that, the relationship between major principal stress and minor principal stress is given by this Mohr circle theory, and from that what we can write down, that sigma 1 is equals to sigma 3 n phi plus 2c root over n phi. This is from the concept of Mohr circle, that from our solid mechanics course itself we know very well the relationship between major principal stress and minor principal stress. when there is cohesion present. Now if cohesion is 0, now C is 0 for cohesionless soil, then we can write down that sigma 1 equals to sigma 3 times n phi, and this sigma 3 is nothing but sigma 1 by n phi. Now what is this n phi is nothing but this is denoted as Ka times sigma V. So this Ka is nothing but 1 by n phi, which is given by 1 minus sine phi by 1 plus sine. So that is the expression for Ka, and n phi is given as tan square 45 plus phi by 2, which came from that failure plane angle with respect to that pole of the failure Mohr circle at the active state of failure. So from this we get this expression or this value. So obviously you can say that Ka is nothing but tan square 45 minus phi by 2. Now if we have a C phi soil, what we will get? In that case, what we will write, that sigma A active state will be written as sigma V time tan square 45 minus phi by 2 minus 2C tan 45 minus phi by 2. Where from we got this? Again, it is from our basic concept of major and minor principal stress relation that I have already derived. Now I do it first for the C equals to 0 case, but if C is non-zero, then this term is present. Then if you want to find out sigma 3, what you will get from this? That's what I did. That sigma 3 will be nothing but, you can write down, sigma 3 n phi will be sigma 1 minus 2C root n phi, or the sigma 3 will be equals to sigma 1 by n phi minus 2C by root over n phi. That's what we did. And the same thing we had written over here, which comes out to be sigma A, which is sigma 3 for the case of active earth pressure, and sigma V, which is nothing but sigma 1, and this is our 1 by n phi, and this is our 1 by root of n phi. So this is the expression for active earth pressure at any depth Z, because the sigma Z is nothing but when there is no surcharge acting on the ground surface, this can be written as gamma Z, and what I said, this symbol is Ka. So I can write it as Ka gamma Z. This gamma Z is sigma V minus 2C root Ka, because this is nothing but root of Ka, we have seen. Therefore, the active state of earth pressure at any depth can be computed by this expression. If it is so, what we can draw the distribution of this active state of earth pressure at any depth like this. So this component is for, this is Ka gamma H if we have height of the wall as H. So at any depth Z, this value of the intensity will be Ka gamma Z. This is this component I am drawing first. Now what about this one? This I have to sum it up, but as a negative. So this is positive pressure, this is negative pressure, this component, which is constant throughout. You can see this is not a variable of Z with respect to depth. So this is 2C root of Ka. And if you combine these two, what do we get finally? So the resultant active earth pressure distribution at any depth will be something like this. So this is our positive This is our negative side, because here it is negative, here it is 0. So obviously we will get here 2c root of Ka, and if we draw this imaginary one, so here to here is essentially our Ka gamma h. So essentially this positive value which you are getting is Ka gamma h minus this 2c root over Ka. So this is our resultant pressure which acts on the wall. Now what happens to this pressure we will come to little later. Before that, let us complete the part of passive condition. Now let us move to the passive state. Let us look at the slide here. So the passive earth pressure against a vertical section with horizontal surface, that is with Rankine condition, smooth wall, vertical face. What happens in this case? Wall is moving towards the backfill. This is the failure plane, and the inclination of that failure plane with horizontal is nothing but 45 minus phi by 2. And what are the forces acting on a chosen plane? Weight of the failure zone. This is passive earth resistance, and this is the soil resistance acting at an angle of phi. So again, these are coplanar and concurrent forces which has to maintain equilibrium. So force equilibrium or force polygon or force triangle can be drawn like this, and based on that one can find out what is the distribution of passive earth pressure with respect to depth. So PP is the total passive pressure one can find out from this distribution. Here again it is the triangular distribution, so it will act at a depth of h by 3 from the base of the wall. Now how to compute for a C5 soil this passive earth pressure? Let us now switch to this camera. So for the case of passive condition, sigma P, what happens? Sigma P is equals to, again I can write sigma V tan square 45 plus phi by 2 plus 2c tan 45 plus phi by 2. Now where from I got this equation? Again, if I take you back to the classical theory of mechanics, let us refer to this same equation, that is the relationship between major and minor principal stress. So here we have seen that sigma 1 and sigma 3 relationship is like this. Now for passive condition, who is sigma 1 major principal stress? That is the passive stress or the lateral stress, whereas sigma 3 or minor principal stress is nothing but the vertical one. So in this case, this formula directly we can use. So that's why the sigma 1 is our sigma P here, and sigma 3 is our sigma V, and this is the rest of the thing. So what is the value over here? I can write now this tan square 45 plus phi by 2, we denote it as Kp. Earlier we denoted tan square 45 minus phi by 2 as Ka, which is active earth pressure coefficient. Now this is passive earth pressure coefficient, and if there is no surcharge on the ground, we call sigma z as Kv, that as gamma z. Sigma V is gamma z plus 2c root of Kp. So Kp is nothing but, in this case, Kp, earlier what we have seen, you can refer it here, we have denoted as n phi. So this is nothing but our Kp. So you can see Kp and Kas, they are inversely proportional. You can see it directly from here. So this is equals to 1 by Kp. That is, active earth pressure coefficient and passive earth pressure coefficient are like this, related like this. So Kp is equals to tan square 45 plus phi by 2. Now what should be the distribution in this case? If we want to draw the expression for sigma P or passive resistance or passive pressure at any height. The first one will be the triangular distribution. So this one is the triangular distribution. Here we will have the value of Kp gamma h when h is the height of the wall. So at any depth of z, the value this one will be Kp gamma z. So that you can calculate from here, plus this component which is not varying with respect to depth. So this is a constant, not varying with respect to depth. If I say this is positive, this also positive here, unlike active case. In active case this was negative, but here it is positive. And how much is the value over here? You can see this one is 2c root of Kp. So what is the net pressure acting on the wall? That is summation of these two. So this is this component. So the total pressure on the wall is acting like this. So here we have the value of Kp gamma h plus 2c root Kp, and on top here you have the value of 2c root Kp. Okay. So that gives us the passive earth pressure distribution as per the Rankine theory. Now let us come back here and look at the slide. What I have already explained, the variation of Pp with respect to depth, and the total passive pressure is half gamma Kph square when there is no surcharge and no cohesion present. And I have completed also those soil which are C and Phi, that is cohesion is also present in that soil. Now what happens if there is an uniform surcharge acting on the ground surface? What that surcharge does, so let us say Q is the uniform surcharge load which is acting uniformly distributed on the ground surface. In that case, that Q will get added to your value of that sigma V. So whatever we have done for active state, let us go back again. So when Q is present, so if I have surcharge present, if you look at here, see when I am now using this black color, a different color which you can make, when surcharge load, uniform surcharge load of Q is present on ground, then the sigma V will be this Ka times gamma Z, and what will happen? Sigma V is now this plus Q. That means our sigma V at any depth will be gamma Z plus Q. So that's why Ka is this one, Ka times sigma Z plus Q. So what I have to do, if surcharge is present, I have to add here one more. I will add here only so that one can understand the distribution of Q. So this is also a constant and it is positive. We can see from this expression. So this I have to add further, which is of intensity Q. So that will get added. So here I have to add one more portion of Q to this, and depending on that value of Q, whether this is positive or negative, that needs to be checked. So this portion Q needs to get added over here for active state. Then passive state, what will be the change? Let us go back to the passive case. If surcharge is present for passive case, the same thing will happen. Here also let me use when Q is present. In that case, the sigma V again changes to at any depth gamma Z plus Q. So this becomes Kp times Qz plus Q. So here we need to add one more component if surcharge is present, which is uniformly distributed, is Q, and you get the total passive pressure with additional term of Q in this. So Q times Kp will come over here. Here you have Q times Kp, because you can see here in this equation Q times Kp is occurring. So this is also Q times Kp. So Q times Kp will get added to that earth pressure component in this passive state. And whereas in the active state, we have already seen that this will get added Q times Ka, that we have seen in this equation. So let us see here Ka times Q. So this Q times Ka should get added. So Q times Ka should get added to this active state of earth pressure. Okay, so now let us look at the slide again here. See, if surcharge Q is acting, this Q times Ka gets added on the earth pressure, and it also says that suppose if our soil is not dry, if it is a submerged soil with a water table existing at a depth of h1 from the top of the ground surface, in that case what will happen? This is your submerged portion, this is your moist portion. You have to consider for calculation of any earth pressure theory, whatever gamma value you are getting, not the saturated value but the gamma effective value or gamma submerged value. Why it is so? Because gamma submerged or gamma effective is the one which is due to the earth, and now remaining pressure is due to the water. So here, as water is present, water is also giving pressure, and for water what is the coefficient of lateral pressure? That is 1. Already we have derived and seen today. So at a depth of h2 for the water table, you will get the intensity here gamma W, which is unit weight of water times h2, and that is again triangular or linear distribution like this. So this is the water pressure which is acting additionally to all this earth pressure. So whenever we are calculating earth pressure, we have to be very, very careful that all these values of gamma must be effective gamma. That means effective unit weight, not the total unit weight, because total unit weight doesn't convey the concept of earth pressure. It takes care of the water pressure and other things also. We should take separately, because the coefficient of lateral pressure is different for two different material. For water it is 1, for soil it is Ka, which is not 1. So if you combine this water pressure here, it will be a gross mistake by considering Ka factor to this water pressure, and as we know Ka is the lowest among the all earth pressure, and we have seen at theory of elasticity K0 is even lower than 1 for NC soil. So Ka also must be less than 1. So if you take this water pressure within this Ka component, you will grossly underestimate the value of the total pressure, because in that case you are designing the wall unsafe for a lower value of pressure, which is not the reality. Reality is much higher pressure will act on your wall. So that's why total pressure computation, one has to be very careful that which value of gamma they have to take for earth pressure and which value of gamma they have to take for water pressure, and then sum them together to get the total pressure which is acting on the wall. So if we have a sloping cohesionless backfill, so same Rankine theory we can extend it further. Earlier we considered the horizontal backface and the vertical backface of the wall and the horizontal ground on the back side of the wall. Now we are considering an inclined ground on the back side of the wall, that is backfill side, which is inclined at an angle of beta with respect to horizontal. Now, the Rankine theory says that this active earth pressure will be parallel to the slope of the ground surface. So whatever is the slope, it will act parallel to it. So obviously PA also should act at an angle of beta with respect to horizontal, but its point of application will be h/3 because it is again linear distribution like this, and the expression for that active earth pressure coefficient now will no longer be phi by 1 plus sine phi, but it will change to this expression because the effect of that ground inclination also come into picture. And using this coefficient of active earth pressure, one can find out what is the total earth pressure or the earth pressure intensity at any depth z. Whereas for the passive earth pressure, this coefficient Kp is no longer 1 plus sine phi by 1 minus sine phi, but it changes to this expression by considering the effect of ground inclination like this. So with this, today we will, and also this portion I have already covered, so I can just show you the slides again. That means for a C5 soil, that is when cohesion is also present, we have seen this from classical relation of two principal stress condition, how the expression for active earth pressure is defined, and that will give us the concept of depth of tensile crack. What is now tensile crack? Let us give a brief today, and tomorrow we will discuss it further. When surcharge is not there, in this case you can see over here, when surcharge is not there, then when C5 soil is present, this component is negative. This component is negative. So at the ground surface, when there is no pressure, this negative pressure is acting, and that negative pressure will continue up to a certain depth until and unless this portion compensate its value and make it to 0. So up to a certain depth, this depth which we call as Z critical, the Z critical is the depth of tension crack, because you can easily expect that because of soil cannot take tension, we all know, and this is the negative stress. So this portion of the soil or this depth of the soil will be under tension. So this depth ZC is called depth of tension crack. Now if you want to try to find out the equivalence of the area of this negative pressure with equivalence of the positive pressure this side, you will also get here another value of equal ZC. So 2 times of ZC we call is at HC, which is known as critical height of vertical cut. What does it mean? That means if you go up to this depth and cut the soil vertically, it will be stable because here negative pressure of coming from laterally from the soil, which is tension in nature, and this is tensile crack, soil cannot take tension, and that equal and opposite negative tension can be compensated with this positive pressure up to the certain depth. So 2C is the 2ZC is essentially the depth up to which theoretically one can go for a vertical cut without any kind of support or any kind of design of retaining wall, because soil property can take it, because this positive soil pressure will get nullified or balanced with this negative soil pressure, but in reality it is not so. So we will discuss that in tomorrow's lecture. Now let me open the forum for discussion for today's lecture, and let us have the chat session, question and answer session with all the participants today, so that they can ask any queries, any suggestion, any doubt, anything in the form of chat or question answer session now in this lecture. In the question answer session, if I can see that there are 3 questions. Essentially there are 2 questions because one question has been repeated, that please elaborate slip lines. The slip lines, the failure planes, I have already described that through Mohr circle, how for this Rankine case of pressure, how we are getting the inclination of the failure plane both in case of active state of earth pressure as well as for passive state of earth pressure. If we go back to those pages, I will probably try to explain it further. Yes. So you can see from here, which we have already discussed in detail, this is the inclination of the failure plane, slip line. This is with respect to the pole you have to find out, that is most important, and which is your principal stress direction, major and minor, that you have to find out. Accordingly you will get which direction it will act, and this is the angle 45 plus 5 by 2, which you can find out from the geometry of this Morse circle with the failure plane. Similarly, for the passive case, this is our slip plane, because in this case the pole of the Morse circle is nothing but this point where passive pressure is acting. So inclination of the failure plane or slip line with respect to horizontal is 45 minus 5 by 2 for the passive state. So I have generalized that and mentioned that with respect to major, principal, plane direction, it is always 45 plus 5 by 2, whether it is active or passive, because in passive case this is the major principal stress, in active state this is the major principal stress, and for them the plane of action, this one it is acting on the vertical plane, this is acting on a horizontal plane. Now the second question was how to calculate the depth of tensile crack. Is there any derivation? Yes. So today, though I have stopped here, in tomorrow's lecture again I am going to continue from this point. So I will definitely derive the expression for tensile crack, but you can see it is from the simple diagram that this is ZC is nothing but our depth of tensile crack. Once you know the value of Ka, 2C, you can easily find out what is this depth of tensile crack. So this is easily derived or easily obtainable from this discussion of today, and tomorrow I will continue from this point. As you are asking again, I said that today we have left it there itself. I have shown through this diagram. Once again I can put it here. Please look here. This is at ground. You have a negative pressure of 2C root over Ka. So the depth up to which it becomes 0, that is nothing but our depth of tensile crack, ZC. From the value of Ka, you can automatically find out the value of ZC up to which depth it occurs. So where that P0 becomes 0, you can see from the slide also. I have mentioned in this slide, if you come back to the slide, this depth of tensile crack 2C by gamma root Ka, that gives us the value of Pa equals to 0. That gives us the critical, that is giving us the depth of tensile crack ZC. So from tomorrow we will start discussing here, because I said this is the theoretical value. In practice we hardly get this depth of whatever we have derived here today. So these are just theoretical or mathematical expression. We will see the proper realistic expression as given by Terzaghi in tomorrow's lecture. Okay. So if there are no further queries, we will stop here today. So thank you. See you all tomorrow at same time. That is 2 p.m. Thank you.